Vamos a pasar a la siguiente. Bueno, si no me equivoco, es José Nuno A. de Bueno, es el nombre completo. José Bueno, adelante, por favor.
Okay, great. So my name is José Nuno Bueno. Good morning, everyone. I will present the paper Longitudinal Control of an Autonomous Truck with Unobserved Gears, which was written by myself in collaboration with Dr. Lucas Marcos, Mr. Kaio Rocha, and Professor Marco Terra. Okay? So the presentation is organized in the following way. First, I will provide a brief introduction about the subjects we addressed in the paper, and then I will present and discuss the longitudinal model of the autonomous truck we adopted for this work. After that, I will present the mode-independent recursive regulator which we applied to solve the longitudinal control problem, and then I will present the simulation results. Finally, we will draw some conclusions about the obtained results. Okay, so let us start. In the past few decades, Markov processes have been receiving more attention from researchers in the control area. Specifically, processes related to autonomous navigation of mobile robots, such as modeling, control, and filtering, can benefit from the Markovian approaches. To name a couple of examples, we have Savasi and collaborators who use the Markovian approach to solve the localization and detection problem of robots in industrial environments. We can also cite Shabra, Mathur, and Bass, who use the Markov-based method to address the navigation problem for a drone controlled via electroencephalographic signals by people with impaired mobility. In general, these Markovian approaches, they assume that the actual active mode is observed at every instant. But the detection of the active mode is not always possible in real world applications. In fact, the systems might be subject to communication and sensor failures, and the detection of the actual mode can demand additional equipment, such as new sensors for redundancy. It's important in the sense to have methods that do not require the observation of the actual active mode while the robot navigates the environment at all instants. In this paper, then, we solved the longitudinal control problem with unobserved Markov modes for an autonomous truck. We modeled the longitudinal dynamics as a Markov process, where each engaged gear indicates the active mode. Then we define an augmented system based on auxiliary variables and formulate an optimization problem based on the classic least squares problem. The solution for this optimization problem we formulate will yield a recursive regulator, which we apply to solve the longitudinal control problem via state feedback. And then we present the simulation results to validate the approach. So the autonomous vehicle we adopted in this work is the scanner truck presented here in figure 1. We consider that the system engages gears from 4th to 10th because the truck is unloaded. Okay? And we define the state space model given here in equation 1. In this model, the states are the drive shaft torsion, Q1, the engine speed given by Q2, and the wheel speed denoted by Q3. Okay? And our input is the normalized engine output torque. And we model the longitudinal dynamics as a Markov process because in order to attain a deterministic model, we would need manufacturer-specific information, such as the set of rules governing the gear shifts and how we would decode and interpret the CAN bus messages. In fact, this information is usually withheld by the manufacturer and it's not disclosed for the community. Therefore, a probabilistic approach can be suitable to solve the control problem when we do not possess this kind of information. Then let us denote by xk the trajectory tracking error between the state, the actual state, and the reference value. And we define the state space model as in equation 3. From this model in equation 3, we can obtain the normalized engine output torque from the control input we compute with the regulator, and the reference torque we collect experimentally. It's worth mentioning that the reference trajectory in this work was collected while we drove the truck inside the university campus. Therefore, the simulations we carry out is based on, since it's based on experimental data, we can say that it's a fairly realistic simulation. Now, let me talk about the mode-independent recursive regulator we applied to solve the longitudinal control problem. We consider a discrete time linear Markov jump system, as the one presented here in equation 4. In the system, the Markov chain is orchestrated by the transition probability matrix P, with the general characteristics outlined here in equations 5 and 6. This set of equations, 5 and 6, is well known in the control field regarding Markov processes. Okay. Next slide. We then define the auxiliary variables zk and vk based on state xk and uk respectively, as shown here in equation 7. Observe that all the entries in zk and vk will be 0 except for those related to the actual active mode. Because of that, we can recover both xk and uk by adding up the entries in the auxiliary variables zk and vk. Here in equation 7, we see that if we sum up all the entries in zk, we will have xk because of the direct measure function here, okay, which is 1 if the actual mode is I and 0 otherwise. Okay? So all the entries will be 0 except the one which is multiplied by the function related to the actual active mode. However, we do not have the information to evaluate this function, the direct measure. Okay. Therefore, from equation 7 and after some algebraic manipulation, we obtain an augmented state space model in terms of zk and vk, which comprises all the modes at once. In this case, the information about the active mode is grouped into the unknown parameter capital delta K. And as we will see in the next slides, the capital delta K will not take part in the solution of the problem we formulate. Okay? Here, as you can see, all the Dirac measure functions are grouped into the capital delta K. Okay? And these Dirac measures, these functions are the information we lack, the information we do not have. Then, to address the regulation problem, we can define the minimax optimization problem in equation 10, based on the augmented model we just defined, with a quadratic cost function given in equation 11. Here in this quadratic cost function, the matrices P, Q, and R are positive definite weight matrices, and the parameter μ is a penalty parameter, also positive. Okay? Then the solution for the optimization problem is provided by Serri and Terra, and is recursively given by equations 12 and 13. In equation 13, we have L as the equivalent closed loop matrix of the system with the regulator. K is the state feedback gain of the regulator. And P is the solution for an algebraic Riccati equation. Observe that the solution requires, I'm sorry, the solution is related to the auxiliary variables zk and vk. Even though the solution is designed for the augmented system, as we saw in the past slides, it's possible to recover the states and inputs xk and uk of the original system. Another important aspect of this solution is that it's not affected by the unknown matrix capital delta K, which, as we saw in the previous slides, contains the information about the active actual mode. In fact, we see here that in equations 12 and 13, there is no capital delta K. It does not take part in the computation of the feedback gains. Therefore, it's possible to obtain the state feedback gain despite the lack of information about the active Markov modes. Okay? Now let us go through the simulation results. For this simulation, we consider a run of 160 seconds with a sampling frequency of 10 Hz. And therefore our time horizon is 1,600. Okay. Also, we assume that the truck starts in the 4th gear with an initial tracking error given by x0. Here, this vector p0 represents the initial probability distribution of the first mode, and since it's 1, 0, 0, 0, 0, we say that we are sure that it starts in the 4th gear. Okay, and we set up the quadratic cost function of the minimax optimization problem with these sets of parameters, the penalty and these weights. And from equations 12 and 13, which provide the solution for the problem, we obtain the feedback gains K. Here, I omit the numerical values of the feedback gain K, because it has 7 rows and 21 columns. It will be just a whole bunch of numbers here. Okay, so I omit. Okay.
I would like to ask you, José, to kindly maybe speed up your last 2 or 3 minutes because of our schedule problem.
Okay.
Thank you very much.
Okay. So in figure 2, we have the states of the closed loop system shown by the black dashed dotted line, and the reference trajectories are given in the red line. Okay? As we see, the regulator successfully tracks the reference trajectories while keeping the small errors throughout the entire run. Okay? Even with the unobserved modes, even if we do not have access to the actual gears. Okay. In figure 3, we have the resulting normalized engine output torques. We see that the approach that the regulator provides feasible torques. We say they are feasible because they are lower than 1, and they're normalized. We would say that the torques are not feasible if these normalized torques were greater than 1. Okay. Therefore, in this case, they respect the operational envelope of the engine. Now, to finish, well, we addressed the longitudinal control problem of an autonomous truck, in which we model the longitudinal dynamics as a Markov process, and we assume that the gear shifts, hence the active modes, are unobserved. We solved the control problem by applying a mode-independent recursive regulator, which and to do such, we formulate an augmented state space model based on auxiliary variables and define the optimization problem. Okay, as we saw, the solution for this optimization problem yields the feedback gains we need to solve the longitudinal control problem. Okay? Based on reference trajectories collected experimentally, we carry out the simulations, and the results show that the system successfully tracked these reference trajectories while requiring feasible torques, okay, that would not damage the engine. As such, the approach has potential for application on other types of ground vehicles whose dynamics can be modeled as Markov jump systems with unobserved modes. Finally, for future works, we intend to investigate the problem of longitudinal control when the truck and the matrices of the truck model are subject to parametric uncertainties. Here I finish my presentation. Thank you all for your time and attention, and I apologize for taking longer than expected.
Thank you very much, José. This was an excellent presentation. It was not your fault. You started late and we're catching up the time. It was very interesting. We only have time for one urgent question. Tenemos solo tiempo para una pregunta urgente para el colega Paulista. ¿Alguna pregunta? Great presentation, says Lucas Barbosa. Nice work from Pablo Monzon. Thank you very much.
Thank you. Thank you.
Any other comments? This is a strange way to conduct a meeting, but we are little by little transforming ourselves into cyber beings. Not exactly, but... and now, if no more questions, we again thank José for his very interesting presentation.